In our previous lecture, we have derived methods for finding multiple roots of a nonlinear equation. We have also derived the implementation of the Newton-Raphson method for a system of nonlinear equations. We have also given what is the importance of a system of nonlinear equations. But polynomial equations form a important class of nonlinear equations. They occur in many application areas. The application of Newton-Raphson method can be simplified if you view it in a different way. Of course, we can apply it directly the Newton-Raphson method of polynomial equation. That means if you just write down what is f of xk, f prime of xk, we can do it. However, the evaluation of a polynomial using its powers as x to the power of n, x to the power of n minus 1 and so on, when the degree is very high, evaluation of a polynomial at a particular value is very expensive and very prone to round off errors. However, if we do it in the evaluation in nested loop, the evaluation of a polynomial in nested loop, that is the Horner's method, then it is going to be less prone for round off errors. Based on similar ideas, we have the methods for polynomial equations separately. Besides, the one more reason why we need methods separately is that we may need all the roots of a polynomial equation. That means if you have a polynomial of degree 20, we may need all the 20 roots of the equation, and if you try to find out by Newton-Raphson each method, each root of this equation, it may be time consuming, and therefore we shall discuss methods specifically for polynomial equations. Now let us write down a polynomial equation of a degree n. So we should denote p for polynomial, n for degree, and it is a polynomial of x, function of x, that we will take it as some a naught x to the power of n plus a1 x to the power of n minus 1 plus so on a n minus 1 of x plus a n is equal to 0, where the leading coefficient a naught is not equal to 0, otherwise it would be a polynomial of lower degree, and we will take all ai's or real constants. They are all real constants. Now obviously the roots of this equation may all be real. So there is one possibility, that one is it has got real roots, or we may have some roots are real and the remaining complex. And the third case is that it has got all complex roots. It has got all complex roots. For example, if we are finding the roots of x square plus 1, we know both the roots are complex. So it is a case arise when the roots are all complex. But we all know that if the coefficients of a polynomial, they are all real, then complex roots occur in pairs. So if we are talking of a complex root, we are talking of complex pairs. So all these roots that we are talking of complex roots they are complex pairs. That means if p plus iq is a root, then p minus iq is also a root of this equation. So it will occur as a pair. Now in the case of polynomial equation, it will be useful for us to know some information about the polynomial. What we mean by is, what is the exact number of roots that this polynomial equation has got, how many complex roots it may have. That means the information that we would be interested in the polynomial is, the one important thing is, what is the exact number of real roots. How many of them are there, and along with their multiplicity. So we would also like to know what is the multiplicity of their roots. And not only that, we know that the number of roots, real roots, we also would like to know what are the intervals in which the roots lies. So we would also like to know what are the intervals in which the real roots lie. Of course, one way for the second part is that we know the intermediate value theorem can be used and we can get it. However, we would like to have an alternative way where it can give us the exact number of real roots that a polynomial equation can have. Now, we already know something from almost from our school studies. There is what is known as Descartes rule of signs for finding the number of roots of a polynomial equation, a bound for the number of real roots in an equation. Let us just see what that rule is, so that we will modify it and then give a rule wherein we will be able to say what is the exact number of real roots. What we do is we take a polynomial, then we write down all the signs in the coefficients with a plus sign, minus sign and coefficient. If any particular power of x is missing, we continue the sign of the previous coefficient. Then we count the number of changes in signs. That we shall say that this polynomial has got this many change of signs. Similarly, we can put x is minus x and can consider Pn of minus x, and then I can do the same thing, find the number of changes in sign in the coefficients. So, what we want to write it, we will say that write the signs of the coefficients. Now, count the number of changes in signs. Now, we will say if a power is missing, then continue the sign of the previous coefficient. Now, let us just take a simple example for this. How we are going to write it? Let us take a polynomial P3 of x is equal to x cubed plus 3x square minus 2x plus 1. And we are not really looking at the magnitude of the coefficients. We are not looking at the magnitude, we are only looking at the sign of the coefficients. So, let us write down what are the signs here. The sign this is plus, this is plus, this is minus, this is minus. Oh, sorry, plus. So, I have got here one change of sign, I got here one change of sign. So, I will say that there are two changes in sign for this equation. Now, let us take a different type of example. Again, I will take a cubic polynomial x cubed minus 3x minus 1 is equal to 0. Now, let us again write the signs in this. So, I have a plus sign here, but x square is missing. So, I can put a 0 here and I can put a plus sign, so that the sign of the previous coefficient shall continue for counting. The next coefficient is negative, next coefficient is negative. Therefore, I have here one change from here to here, or you can look at from here to here, that there is one change in sign. Now, based on these signs, we have what is known as the Descartes rule of signs. It is called the Descartes rule of signs. What it states is the number of positive real roots of a polynomial equation cannot exceed the number of changes in sign, right. That means, I will explain it again. Let us write it. It is the number of positive real roots cannot exceed the number of changes in sign in P n x. Now I can do the same thing with Pn of minus x. Then I will have the conclusion that the number of negative real roots cannot exceed the number of changes in sign in Pn of minus x. So I can go for the negative roots. So the number of negative real roots cannot exceed number of changes in sign in Pn of minus x. In other words, this rule gives us an upper bound for the number of real roots. For example, if a polynomial have got 5 changes in sign, it will say in Pnx, then it will say it may have 5 real roots. It will say it may have 5 real roots. Since the complex roots can occur in pair, we can say that all the 5 are real, or 1 real, 4 complex, that is 2 complex pairs, or 3 real, 1 complex pair. That is because complex has to come as pair. So you will have to reduce by 2. So either it will have 5 real roots, or 3 real roots 2 complex, 1 real root 4 complex. So that way we can give the upper bound for the number of positive real roots as well as for negative real roots. Now if you I will just repeat this example. Let us have a look at this same example again. So let me just write that example again. Let me take this P3 of x. This is your x cubed plus 3x squared minus 2x plus 1 is equal to 0. Therefore I have the for P3x, let us write down the signs of this. So we have plus, plus, minus, plus. So we have got here 2 changes. Now let us also write down what you have P3 of minus x. P3 of minus x. Now P3 of minus x gives minus x cubed. Put x is minus x here. I will have plus 3x squared. I will have plus 2x here, and we have plus 1 here. Now I will look at the signs of the coefficients of this particular polynomial. So I have a negative sign, plus sign here, plus sign here, plus sign here. So I have got 1 change of sign here. Therefore we conclude that this polynomial has got 2 positive real roots or 0 real roots, real positive roots, and 1 complex pair, and definitely 1 negative root. Because if you have a odd degree polynomial, an odd degree polynomial will always have a real root, because the complex roots have to come as pairs. Therefore if there is 1 change of sign, there cannot be a complex root, because a pair has to come. Therefore 1 change is there, means surely that this equation has got 1 negative, we are guaranteed of 1 negative real root. Whereas in this case we have 2 changes of sign, therefore it could be 2 positive real roots or 2 minus 2, that is 0 real roots and a complex pair. Therefore we conclude for this particular polynomial, it has got 2 real roots, it has got 2 real roots, 2 real roots, and 2 real roots, we will also say positive, and 1 negative real root. That is one conclusion. Alternatively, it has got no positive real root, 1 negative real root, and a complex pair. And a complex pair. Now as I mentioned earlier, an odd degree polynomial will always have a real root. So an odd degree polynomial has always a real root. Whether the real root is positive or negative, that we can decide upon by testing these changes in signs, but an odd degree polynomial always has got definitely a real root. Now to understand it better, let us repeat the second example also, which we have discussed earlier. So let us write that example.
So that odd degree polynomial has real coefficients.
One, yes, already we are talking of only real coefficient problem. When once the coefficients becomes complex, then complex pairs need not occur. When once the coefficients are complex, then the complex roots need not be pairs, it can become alone. So therefore the discussion that we are making, that the number of real roots will reduce by factor of 2, it will not come into picture this one. So we will be only considering the real coefficients. So let us take the second equation, p cubed p3x is x cubed minus 3x minus 1 is 0. So again let us take the signs in this particular one, which we have done earlier. This is a plus sign, a 0, so it which continues a plus sign here. I have a negative sign, a negative sign, therefore I have got one change in sign in this. I have got one change in sign, therefore we are sure that this equation has got one positive real root, therefore it has one positive real root. Now we consider whether there is any negative root, so I will put x is equal to minus x in this, so I will get minus x cubed plus 3x minus 1 is equal to 0. Now I will write down the signs again. This is negative, now x square is missing, so that will be 0, so sign, negative sign will continue. Then I have a plus sign, I have a negative sign, so I have one change of sign here, I have one change of sign here, so I have got two changes in sign here. Therefore I conclude that the polynomial has two negative real roots or a complex pair. Now in totality, therefore we will be able to say that this polynomial has got one positive real root and two negative real roots, or one positive real root and a complex pair. Now therefore the Descartes rule of signs gives us only a bound for the number of real roots. If a polynomial has got 10 changes in sign, it will at the most say that it may have 10 real roots, but it will not say that it will have exactly 10 real roots, or it has got exactly 6 real roots. And this particular aspect of the exact number of real roots can be obtained by forming what is known as Sturm sequences and using what is known as Sturm theorem. It is a very simple application. So let us define what is a Sturm sequence. Now we start with a given polynomial. So f(x) is a given polynomial. Now let us differentiate f(x) and denote it by f1. So we will differentiate f(x) and write it as f1x is equal to f prime of x. Then what I do? I will divide f(x) by f1x, divide f(x) by f1x and find its remainder. Find the remainder of this ratio. Find the remainder of this particular ratio. Put an opposite sign to this remainder and call it as f2x. So let us call this remainder as r, let us say. Then I will define f2x as minus this particular remainder. I will take this as minus remainder. all right, of f x upon f prime x. Now, I repeat the procedure, that is I will take f1x, f2x, I will divide f1x by f2x, this division is ordinary division, find the remainder, put the opposite sign to it and call it as f3x. So, I would define f3x as opposite sign of the remainder of f1x by f2x. Therefore, I will continue on until when once you see, you can see that f(x) is a polynomial of degree n, f1x is f prime, therefore, is a polynomial of degree n minus 1, divided it out, remainder we have got, each time I am dividing by polynomial of 1 degree lower. Therefore, after some stage, after n stage, I am going to get a constant. So, we will repeat until a constant is obtained. So, repeat until a constant is obtained. Now, this gives us a sequence of functions. So, let us write down the sequence of functions f(x), f1x, f2x, so on f1x. This sequence is called a Sturm sequence. We call this as the Sturm sequence. We can see that right through we are interested in only the sign of the remainder. Therefore, when I get f2x as a rational coefficient in the leading term, since we are interested only in the sign, I can throw away or remove that particular coefficient from there. Let us suppose I have got 16x plus 64, 16x square plus 64x. I can take common factor 16 and write this as x square plus 4x, and in the next step I can throw away the 16 because I do not need to use it, because I need only signs. Therefore, any particular factor that is there to me can be dropped in the next computation, so that the computation will become easier for hand purposes also, where if you want to do by hand, we will be able to do by hand also. So, at any particular stage we can say we can multiply or divide by a positive constant, so that the rational coefficients can be removed. That, for example, you have got it, the leading coefficient as 2 by 3. So, to do the computation next step it will be difficult. So, we can throw away by 1 by 3. So, if I remove through 1 by 3, I am multiplying by 3 throughout. That means I will take it as 2x square plus 3x. So, it is easier for me for the dividing in the next stage. Therefore, we can multiply or divide by any positive real constant to remove some of these the rational coefficients. So, we can, let us say we can multiply or divide the elements of the sequence by any non-zero positive constant to avoid some rational coefficients. So, the main idea here is the to remove the rational coefficient, that is simplify over divisions. Now, we give the what is known as the Sturm's theorem. So, let us write it in the next sheet. Let us define what is the Sturm's theorem. Now let me just give the result. The result is so simple. We start with your polynomial fx, we construct the Sturm sequence. I take any value x is equal to a, any number x is equal to a, substitute x is equal to a in all these functions. Then I study the number of changes of sign in this Sturm sequence. Let us call this number of changes as some v of a. If of course f of a is 0, then it is a root. We are assuming f of a is not 0. I take another value x is equal to b, substitute, and then again study changes in sign. The difference in these two numbers, that is v of a minus v of b in magnitude, will give me the exact number of real roots in the interval ab. This will give you the exact number of real roots. If the number of changes of sign at x is equal to a is 5, if the number of changes of sign in x is equal to b is 3, then the number of real roots between this is 5 minus 3, that is 2 exact real roots are there. Now I can further subdivide this and then find the exact number of real roots in that particular thing. So I can go on subdivision and then find the number of real roots until I get a required small interval. So this will give the way of finding the exact number of real roots. So for this we first of all form this Sturm sequence. Then let us take any number. So let x is equal to a, and of course f of a is not equal to z. I mean what we are saying is f of a is equal to 0, x is equal to a is a root. So therefore we need not consider this particular case. Now we will say let Va be the number of changes of signs, be number of changes in signs in this Sturm sequence. Similarly, let v of b be the number of changes of signs in the Sturm sequence for x is equal to b. Now we have already mentioned that if any function is missing in between, that means a function turns out to be 0 at x is equal to b, we continue the sign of the previous function. Just as we are counting the signs in the coefficients, here also we say that if any function, if any fi is equal to 0 for x is equal to a or b, then we continue the sign of fi minus 1. That means in the Sturm sequence that we are following f1, f2, f3, we have got any fi is equal to 0, we just take the sign of the previous coefficient, previous function, and then continue in the counting in the sign of this one. Now once you are able to find this number of exact roots, then we will be able to find the number of complex roots. It is possible for us to modify it slightly and find the multiple roots also. I will just explain what would happen in the, if there is a multiple root, what happens to the coefficient. There will be change in coefficients. Once you decide the roots, then I can, total number of roots for the polynomial equation are n. So I can subtract this exact roots that we have real roots, and then I have the number of complex roots. So using this theorem I will be able to tell exactly the number of positive real roots, exact number of negative real roots, and the exact number of complex roots. So that is the importance of the Sturm theorem. Let me take this example, 4x4 2x squared minus 1 is equal to 0. So, I want to state the number of roots for this particular equation. 4x4 plus 2x squared minus 1 is equal to 0. So, I just have the first function f(x) is equal to 4x4 plus 2x squared minus 1. I differentiate this and put it as f1. So, this is 16x cubed plus 4x. Now, we are saying that there is a common factor here which I can throw it away. So, I will write it as, or I will take it as f1x as 4x cubed plus x. So, here we have 4 is removed. So, this is what we said, we need not consider that factor at all, we can just remove that factor from f1x. Of course, we are removing only the positive constant. Now, I will write down my f2. Now, I will divide fx by f1x, that is 4x4 plus 2x squared minus 1 divided by 4x cubed plus x. And this division which we are talking of is the manual division, is ordinary division that we can do. That is, I can see that I will have to multiply this by x plus subtracted x squared minus 1 divided by 4x cubed plus x. So, this is nothing but we can just check it up, we can 4x to the power of 4 x square plus x square 2x square minus 1. Now, what we are stating is the remainder of this is x square minus 1. So, the remainder of this is this quantity. Therefore, I will denote f2x the opposite sign of x squared minus 1. Therefore, I will write f2x is equal to minus sign of remainder, that is minus sign of x squared minus 1, that is equal to, let us write it as minus x squared plus 1. Now, I have determined f2, now I will determine my f3. Now, I will write down f1x divided by f2x. So, I have to divide f1x by f2x. Now, f1x is, we have here 4x cubed plus x, f2x is minus x squared plus 1. So, I can just write this as minus 4 times x plus 5x by x squared plus 1. So, this is 4x cubed minus 4x plus 5x, that is plus x minus 1. Therefore, the remainder for this would be the remainder is this quantity, that is your 5x. Therefore, I would define my next function f3x is equal to minus of the remainder, that is equal to minus 5x. I can again drop 5, I can throw away the constant 5. So, I can take this as, or f3x is equal to simply minus x. I can remove the positive constant 5 from here. Then I divide f2x by f3x. f2x is minus x squared plus 1 divided by minus x. This I can write it as x plus 1 upon minus x. Remember, I would like to retain this f3x as minus x in the denominator. I will not bring minus sign here, because the denominator should be our that function that we are tackling, that is your f1, f2 or f3, whatever the function. So, the denominator I will keep them as minus x itself and consider the remainder as the numerator of this part. Therefore, f4x is equal to minus the remainder of this is equal to minus 1. in general we will reach f1x when we produce a constant. We started with the polynomial degree 4, so therefore we continue up to f4 to produce a constant over here. Therefore we now have got the Sturm sequence. Let us now write down the Sturm sequence here. The Sturm sequence will be fx, that is a given function 4x4 plus 2x squared minus 1. f1x is the next of these functions 4x cubed plus x. f2x is the next function, that is minus x squared plus 1. f3x is equal to minus x, and f4x is minus 1. Now what I need to do here is I need to study the changes of sign in this one and then locate the roots. So let us look at the, let us form a table. So let us find out what are the sign changes in this sequence, sign changes in the sequence. Now let us write down the fx here, f1x, f2x, f3x, f4 of x and v of x. V will be the number of changes in sign in this one. Now let us start with the number, let us put x also here. Let us start with minus infinity. When I put minus infinity in fx, this is minus infinity to the power of 4. So this will have the positive sign. So I will have a positive sign in fx. When x is minus infinity in f1, it is all negative. So it is going to be a negative sign. This is minus x square, therefore it is always going to be minus infinity. This is minus x, therefore this will be plus infinity. So they will have a plus sign. f4x is negative constant, therefore I have one change of sign here, I have another change of sign here, I have one more change of sign over here. Therefore number of changes of sign with at in minus infinity is 3. Now we can study, I will reduce the amount of work, we can have a look at this closely. For mod x greater than 1, this is always going to be negative. When x is negative, this is always going to be negative, and when x is negative, this is always going to be positive, and this is always negative. So when mod x is greater than 1, the signs of all these have been fixed, and in fact for this also it is fixed because this is 4 times x4. So this is always going to be positive. Therefore when mod x greater than 1, these signs are always almost fixed. So we do not have to see what happens at minus 10, minus 5, minus 3 and so on. We just pick up a number greater than magnitude of greater than magnitude of 1 in on the negative side and then study what happens. Like for example, I can take minus 2. This we have already discussed. So if you put minus 2, I will have a plus sign here, minus 2 I will have a minus sign here, and if I put minus 2 in this, this will be again minus sign, this will be a plus sign, and this is a minus sign. So I have chosen a number which is in magnitude greater than 1, and therefore the number of changes of sign in this is again 3, which shows that there is no negative real root beyond minus 2. Let us take minus 1. If I take minus 1, fx is still positive, and this is negative, and this is a 0, x is minus 1, this is a 0. So I would continue the sign of the previous coefficient. f3 is positive, f4 is negative. Therefore it still has one negative sign here, and one change of sign, one change of sign, one change of sign. There are 3 this. Therefore still there is no negative root between minus 1 and minus 2 also. So let us take 0. At 0, f4 is negative, f1 is 0. So, I will continue the negative sign of the previous coefficient. At 0 this is positive, at 0 this is 0, therefore, I continue the previous sign. F4 is negative. Now, I have a change in sign minus to plus, I have a change in sign from plus to minus here. I have got two changes in sign. Therefore, I now have got V of minus 1 minus V 0 in magnitude is 1. Therefore, this is one change in sign over here. Therefore, we will conclude a little later. Therefore, there is a negative root between 0 and minus 1. Then let us take 1. If I take 1, this is positive, this is positive, F1 is positive, F1 is positive. Then if I take F2, this is 0. So, I continue the plus sign, I continue the plus sign. When 1, this is negative and this is also negative. Therefore, I have one change in sign here. Again, there is a change in the value of V of x. Therefore, there is a root between 0 and 1. Again, when mod we already checked that mod x greater than 1, these are not changing the signs. Therefore, I can immediately go ahead and have the same result that we have over here. I can put 2 here now and then write down the signs that we have already we have earlier. This is going to be plus sign, this is going to be plus sign, this is a negative sign, a negative sign and a negative sign. Maybe I would just bring this sheet over here and put it here. So, we can see that when x is equal to 2, this is a positive sign, this is a positive sign, this is a negative sign and a negative sign. So, I now got one change of sign only here. We can conclude positively from this result that there is one negative real root between minus 1 and 0, one positive real root from 0 to 1, the other two must be a complex pair. Therefore, we have got here positive real root, there is 1 in 0 1, there is negative real root, there is 1 in minus 1 0 and a complex pair. Therefore, from this example we have seen it is possible for us to tell exactly the number of real roots, and this term sequence will then automatically give us the interval in which the root lies. Now, in a general problem maybe you may not take that closely, you may take a larger interval say between 0 and 10 depending on this, or 0 and 5, and you will find that between 0 and 5 there are 3 real roots. Now, if there are 3 real roots, then we can reduce the interval further and to locate the interval in a particular required interval, but it will give us the exact number of real roots. We know now that the root lies in an interval and the exact number of real roots is known. Now, how to find these real roots? The problem is to now to how to find these roots. Now, I would explain the philosophy that is used in deriving some of these methods. Now, if let us assume that the exact roots are say xi1, xi2, xin. And let us say that these are the roots of the given polynomial xi1, xi2, xin. If these are the exact roots, then the polynomial can be written as x minus xi1, x minus xi2, x minus xin. So, polynomial can be factorized because these are n real roots, and let us take these let us take them xi1, xi2, xin. We have taken this as a real and distinct. When once I take these the roots as real and distinct, then I can always factorize them and write it as x minus xi 1, x minus xi 2, x minus xi n. If they are real and have multiplicity, I can also write even then. Let us suppose that xi 1 is multiple root of multiplicity, let us say v 1, and let us also take xi 2 as a multiple root of multiplicity v 2, and let us take all of them are multiple roots. Let us take that it is a multiple root this. Of course, the sum of this has to be n, because the total number of roots are n. So, we must have the condition that the sum of all this is equal to n, the total number of roots are n. That means, I can write down my polynomial as equal to x minus xi 1 to the power of v 1, x minus xi 2 to the power of v 2, and so on, x minus xi r to the power of v r. What we would therefore would do is, if I want a real root, I will try to extract a real root from that particular equation. Now, I am using the word extract in a slightly different sense from what we are using Newton-Raphson method. In Newton-Raphson method, we are saying find the real roots of this particular thing, but what we want to talk here is we want to extract a real root from the polynomial equation and then produce also automatically what will be the polynomial or the that will be obtained by removing that root. That means the deflated polynomial. Suppose a polynomial of degree 10 we have, if I extract a factor from there, one factor from there, linear factor, what is left out is polynomial of degree 9. So, therefore, we shall say extraction of a root would imply automatically we are talking of the deflated polynomial also that will come out of this particular method that we are constructing it. Therefore, it is possible for us to extract one root or a root which is of multiplicity v 1 starting with any particular procedure, and the method would automatically take care of giving us the deflated polynomial, so that we should work on the deflated polynomial, because if we may just close down in a minute. If we have a polynomial of degree 50, if I want all the roots of this polynomial, even though I know the location of the 50 roots, I would not attempt to use the method on the polynomial of degree 50 times. I would extract a root, deflate it, get a polynomial degree 49, get to the next root, deflate it, get a polynomial of degree 48. So, each time deflation will reduce the degree of the polynomial. It will also of course reduce the amount of computation that we are performing, and another very important thing that it does is that it will not allow the root to go again to the back to that original root. Suppose x is equal to say 0.5 was a root, I have extracted the root. If I had repeated the method on the original polynomial, it may be possible that you are again going to the same root 0.5, but not to the next root. But here we are, when once you deflate it, you remove that particular root from the p n x, we have got the next degree polynomial, we are definitely going to approach the another root for which we are taking a starting value from a given point. Therefore, this reduces the computation also. It is called the process of deflating the polynomial and then getting all the roots. And finally, after some stage it will come down to a quadratic factor, and that quadratic factor we can find out the two roots of the quadratic factor and get all the roots. Okay, we will conclude for today.